Hi, I'm Divya. Today we are going to discuss thermal atomic layer etching of gallium nitride, and the contents are as shown below. First and foremost, what is GaN? GaN is known as gallium nitride, which basically belongs to group 3 and group 5 elements. The properties of gallium nitride are wide band gap, larger breakdown voltage, high electron mobility. Hence, it is widely used in today's semiconductor technology. What is wide band gap? It's a gap between the valence and conduction band where electrons eliminate during that jump from valence to conduction band. This can be achieved by the means of thermal, and these are mainly used in to produce smaller devices which are more faster, more efficient, and those devices have an ability to withstand high pressure and high temperature. The high electron mobility property is used in RF components, so because it can handle high switching frequencies. But the disadvantage of gallium nitride over silicon is it has low thermal conductivity comparatively, and the breakdown voltage for gallium nitride is 3.3 megavolts per centimeter. Gallium nitride is very difficult to dry etch because of strong atomic bonds. That's the reason the most aggressive gas like chlorine is usually used to etch gallium nitride. Silicon dioxide and nickel are also used to slow down the etch rate. Some other gases like boron trichloride could increase the anisotropic profile, whereas chlorine with argon eh, could increase the etch rate. But there are certain defects like inclusion on the surface of gallium nitride which could impact the LED light emission performance, and also it results in defects in band structure where it causes the mid-gap states, thus resulting in recombination of carriers and resulting in phonons instead of light. Whereas wet chemical etching is even more difficult because we're immersing the samples in either acid or base and modifying that material. So it results in isotropic and non-uniformity. Iron milling technique. Iron milling technique usually for hard materials like gallium nitride, it could crack easily and the surface is damaged by the mechanical polishing method. Why ALE? Because of certain limitations in continuous simultaneous etching, we choose ALE. Certain example is reactive ion etching, where reactive ion etching uses the plasma to generate large number of chemically active species and interacting with the material surface to form volatile products. But the limitation is non-uniformity when the surface composition might change. And in some high electron mobility devices, it is very difficult to etch because we wouldn't have a good control over it. And high energy could also lead damage to the substrate. Atomic layer etching is known as removal of thin layer of material by a multi-cycle process or removal of a material at atomic scale. There are two types, plasma ALE, thermal ALE, and both are going to be discussed further in brief. Plasma ALE. Plasma ALE is known as cyclic etching process of gas dosing or ion bombardment that removes material layer by layer. Here is a video how the plasma ALE is performed. Initially, the substrate is dosed with the etching gas and then reacted with the etching material, and then all the residual gases are removed. After this process, the surface is bombarded with ions. Sometimes it might even lead to defects such as cavity or columnar defects. Cavity defects usually occur due to ion bombardment, whereas columnar defects occur in passivation of nanopipes present in the bulk material. The etch rate of plasma ALE is usually high. Thermal atomic layer etching is a technique that uses sequence of self-limiting reaction for thin film etching, and this is similar to ALD except it is reverse, and it has two steps. One is surface modification and surface removal as shown in the next figure. Surface modification A is due to surface chemisorption layer formed on the edge surface by a precursor vapor self-limiting absorption, whereas the surface removal B is a semi-chemi-absorption layer converted to volatile etching product by introducing proper precursor. There are four cycles which is known as absorption, excess reactant evacuation, surface removal, and volatile reaction products evacuation. The first and the third one indicates the self-limiting steps, whereas excess reactant evacuation and reaction product evacuation includes velocity limited step. The etch rate per cycle is usually constant here. For thermal ALE, it is separated to half reaction that helps to improve the interaction between the surface modification A and surface modification B to control the order of surface reaction and make the reaction self-limiting as possible, and also opening the thermal ALE window. This discontinuity between the reaction helps in avoiding the formation of a thick mixed layers and also restricting the unwanted gases to react in plasma. Here we are discussing how gallium nitride reacts with xenon difluoride and boron trifluoride. In the first, xenon difluoride fluorinates the gallium nitride. This reaction is spontaneous and it results in the negative Standard free energy. This xenon difluoride, when reacts with gallium nitride, it gives gallium fluoride. And this gallium fluoride will be stable until 550 degrees Celsius in vacuum. Then the inert gases are used to remove the unwanted gases, and the ligand exchange mechanism is performed using boron trichloride to produce gallium trichloride to etch the surface. Whereas in boron trichloride reacts with gallium nitride, it performs two steps. One is converting gallium nitride to boron nitride, then fluorinating this boron nitride layer to boron trifluoride. Hence, it concluded that the boron trifluoride and xenon difluoride both are required to etch gallium nitride. Only xenon difluoride cannot etch the gallium nitride. First, we're going to discuss the thickness of gallium nitride film with respect to particular temperature and various temperature. Gallium nitride thickness is usually measured in in-situ spectroscopy ellipsometer. In the first figure, gallium nitride is exposed to xenon difluoride for 20 seconds at 40 millitorr, and then boron trichloride for 0.5 seconds at 50 millitorr pressure. But in between both, the gases are purged with argon for 60 seconds at 190 degrees Celsius, and the etch rate was 0.55 Armstrong per cycle. After multiple experiments, the etch rate noted varied between 0.5 to 0.59 Armstrong per cycle, but the etch rate was much less than the gallium nitride etch rate and plasma ALE using chlorine. Whereas in figure B, with the same conditions, same exposure time, only considering the film thickness at 3093 Armstrong at various temperature, it showed that the etch rate increased linearly. This increase in etch rate might be because of the thick fluoride layer formed at high temperature, and also this fluoride layer is removed by the ligand exchange mechanism with boron trichloride. Here we are going to discuss the etch rate versus the number of doses. In the first figure, the boron trichloride was exposed at the constant pressure of 50 milliliters for 0.5 seconds while varying the number of xenon difluoride doses, and exposing xenon difluoride at 20 seconds at 40 milliliters. And it was noted that the etch rate was initially slow, but it increased with increased number of xenon difluoride doses. And at some point when was xenon difluoride dose was 6, the etch rate was 1. This could result or affect the conformality of gallium nitride ALE in high aspect ratio structures, whereas in figure B, the condition was same except that the boron trichloride dose was varied. Etch rate, here the etch rate saturated very quickly, and due to this lack of boron trichloride exposure, the dependence argues for the ligand exchange mechanism for gallium nitride ALE. If boron trichloride converts gallium nitride to boron nitride, then the etch rate should increase with the boron trichloride pressure. But then in this figure, it reveals that the gallium nitride etch rate do not increase with the boron trichloride pressure. The boron trichloride pressure at 250, at 500 and 1000 milliliters were held statically for 5 seconds, and xenon difluoride pressure was maintained at 40 milliliters for 20 seconds. At 195 degrees Celsius, the etch rate noted was 0.56, 0.57, 0.62 Armstrong per cycle, whereas for 250 degrees Celsius, the etch rate noted was 0.63, 0.68, 0.63, which was almost constant. This constant gallium nitride etch rate argued against the conversion mechanism and supported ligand exchange mechanism. And it also concluded that both xenon difluoride and boron trichloride were required for ligand exchange mechanism. Additional experiments were performed using HF and SF4 as a fluorination reactants for gallium nitride. Thermodynamically, it could fluorinate gallium nitride to gallium fluoride, but then there was no evidence that the gallium nitride was etched even after 20 cycles. Figure here displays the gallium nitride thickness versus the number of reaction cycles at 250 degrees Celsius. First, the NF3 was dosed into the chamber at the pressure of 40 milliliters for 25 seconds. After some time, boron trichloride was dosed into the chamber for 0.5 seconds at the pressure of 50 milliliters, and it showed that the etch rate is 2.85 Armstrong per cycle over 20 cycles. After performing the repetitive experiments, it showed the etch rate varied between 2.5 to 2.9 Armstrong per cycle. And it was concluded that the gallium nitride etch rate are much higher than the etch rate of 0.65 Armstrong per cycle at 250 degrees Celsius obtained using xenon difluoride and boron trichloride. This higher gallium nitride etch rate might be because of the thicker fluoride layers formed by the fluorine radicals.